So let's discuss about two important parameters in the fluid kinematics: the velocity potential and the stream function. So these are basically the functions of xy function of space, which describes or which represents, which tells you something about the flow pattern. So flow pattern quantities, they tell you about the flow pattern. Okay, so first is velocity potential. Let's see how it is defined and what it means. What is the physical significance of velocity potential? Okay, so now before just understanding this, what is velocity potential, we saw that for an irrotational flow, your curl of V, your curl V has to be 0. Curl of velocity vector has to be 0. Well, now from vector calculus we have one important derivation, which means that curl of a gradient of a scalar field is 0. So this is an important mathematical result from vector calculus, and this is the definition for irrotational flow. So if I understand 1 and 2, what I means is that a velocity vector I can write in terms of grade phi. So I just defined velocity field in terms of grade of minus grade of phi. Okay, I mean the minus will not change this, because if you replace v bar as minus grade phi and take out minus common, it's still going to be a case of rotation. So but what is the importance of the phi? What if I define in this way, del phi, grade is the gradient of phi, so it means that dou phi by dou x minus dou phi by dou y, dou phi by dou z. That means the components of v bar, which are ui plus vj plus wk, they will become these. Okay, so what it means is that for a flow to take place, so when a flow takes place, it takes place in the decreasing value of phi. So fees are all like this, the scalar. Okay, let's say phi, so you have phi 1, phi 2, phi 3. So what it means is that flow takes place in the decreasing direction of phi. So what it means is, if I am taking, if a flow is taking place like this, that is the correct direction of flow, because it takes place in the decreasing direction of phi. So if the velocity vectors are like this, that means phi is decreasing in that direction. So that is the significance of this. So flow takes place in the direction of decreasing phi values. So phis are all scalar functions of x, y, z. So depending on the pattern, if I can get, so if phi pattern is given, I can just build up that. Okay, now for incompressible flow, we already saw that for incompressible flow, your divergence of velocity vector has to be 0, and velocity vector for irrotational phi is nothing but minus del of phi. So this is minus del square phi equal to 0, or del square phi is equal to 0. So you get that Laplacian equation for an incompressible flow. So if you happen to find out phi that satisfies Laplace equation, it means it is a case of irrotational flow. So if there it's phi that satisfies Laplace equation, because this satisfying incompressible is that is the minimum requirement. A flow is incompressible. Okay, so a phi that satisfies Laplace equation, that means the flow exists, and if a flow exists, it is an irrotational flow, because So flow exists or not means it is incompressible, we assume that flow exists. Okay, and if flow exists, then we say whether it's rotational or irrotational depending on this. So if you happen to find out phi that satisfies Laplace equation, it is case of irrotational flow. So this is about velocity potential. Now let's come to another important thing called stream function. We've already seen what is a streamline. Streamline is nothing but the imaginary curves where the tangent to the curve is the velocity vector. So if you happen to build imaginary curves in the flow pattern such that any point to tangent to these curves gives you the velocity vector, that is your streamlines. A stream function is nothing but its equation of this streamline. So we have already discussed that the equation of streamline for a 2D flow looks like this. So if I just rearrange this, I get this is my equation of the streamline. So now suppose if I define my u to be some derivative of psi with respect to y and v some derivative of psi with respect to x minus, and if I so these are just the definition. If I happen to keep u and v in this way and substitute in this, it will satisfy, right? So u is dou psi by dou y dy minus dou psi by dou x dx. This is nothing but d of psi, which is 0. That means psi is constant along the streamline. So if I define u and v in this way, I get psi, which is constant. So that means along this curve psi is constant. Psi1 is some value psi is some value c1, c2, c3. Okay, so in this way I can build up a scalar function which represents the streamline. So psi is constant along the streamline. Okay, so now these are the two velocity potentials. So in a velocity potential, so if my psi's are like this, let's say, so this is psi is equal to c1, psi is equal to c2, psi is equal to c3. The flow is taking place in this direction. The velocity potentials will be perpendicular to this, and those will be in the decreasing direction. So phi, this is, let's say, phi1, phi2 and phi3. So phi1 is greater than phi2 is greater than phi3. So flow is taking place in the decreasing direction of velocity potential. And so this is how, so your curves of velocity potential and stream functions are perpendicular to each other. And stream function, that can be just proven, stream function are perpendicular to each other. So this is basically a flow net. So let's solve some problems on this part.